Welcome, my friends! Today we will be introducing hypothesis testing. Let's begin with a motivating example. Suppose I come across a coin on the side of the street. It isn't a coin that I recognize, so I decide to pick it up. There are two sides to this coin, which I might call heads and tails. For fun, I decide to give the coin a few flips. The first flip, heads. The second flip, heads again. Third flip, heads. That's weird. 3 heads in a row. By all appearances, the coin seems normal. I would expect there to be a 50-50 chance of the coin turning up heads on each flip. You might say that my default position, my initial belief, or perhaps my null hypothesis is that the coin is fair. Let's say that I keep flipping the coin. Flip 4, heads. 5, heads. 6, 7, 8, heads, heads, heads. Alright, something's going on here. Either I have witnessed a very rare and improbable event, flipping 8 heads in a row on a fair coin, or maybe my null hypothesis is incorrect. Maybe we should adopt a new hypothesis, an alternative hypothesis, that the coin is not fair. When only 3 heads had been flipped in a row, that might not have seemed all that unusual. It isn't all that unlikely for a fair coin to turn up heads 3 times in a row. But at some point, the sample data becomes so inconsistent with the null hypothesis that we must adopt a more reasonable assumption, the alternative hypothesis. At what point we adopt the alternative hypothesis might be different for everyone. Maybe one person needs to see 5 heads in a row to conclude that the coin isn't fair, whereas someone else might want to see 15, or perhaps a high percentage of heads or tails on a large sample of flips, like 100. This example exemplifies the statistical procedure of hypothesis testing, which is the bedrock of the scientific method and one of, if not the most important applications of statistics. Hypothesis testing allows us to challenge the status quo by gathering data. If the data is highly inconsistent with our prior assumptions, we throw out our old hypothesis and adopt a new one. Now that you have a little bit more intuition as to what hypothesis testing is all about, let's look at the definitions and procedure in more detail. In any hypothesis test that we complete in statistics, there will be 2 hypotheses. The null hypothesis is denoted by the capital letter H with a subscript 0, and typically refers to the status quo, the default position, or perhaps a historically accepted claim that the researcher would like to challenge. The alternative hypothesis is denoted with the capital letter H with a subscript A or 1, and typically represents a claim that contradicts the null hypothesis that the researcher would like to try to prove. Every hypothesis test contains both a null and alternative hypothesis. After data has been gathered, there are 2 possible decisions. We fail to reject the null hypothesis if the data is fairly consistent with the null hypothesis. This doesn't mean that the null hypothesis is necessarily true, it just means that our data does not suggest that it's false. We generally try not to say that we accept the null hypothesis. Accepting the null hypothesis makes it sound like we know for sure that it's true. It's much more accurate to say that we fail to reject the null hypothesis. We reject the null hypothesis in favor of the alternative hypothesis when the data is very inconsistent with the null hypothesis. This doesn't mean that the alternative hypothesis is certainly correct, it just means that our current data suggests that the alternative hypothesis is likely correct. New data might come later in the form of more studies to reaffirm the alternative hypothesis, or perhaps it might be disproven. The phrases fairly consistent and very inconsistent are a bit loose here, and we end up making our final decision based on probabilities, which we will discuss in more detail in future videos. Most hypothesis tests will be left-tailed, right-tailed, or two-tailed, which is determined by the alternative hypothesis. The best way to understand the difference between the 3 types is through an example. Let's say a can of pop, or soda, depending on where you're from, is stated by a company to contain 12 ounces of liquid on average. This takes the place of the default, historically accepted position, and will therefore be our null hypothesis, mu equals 12. Now, suppose you would like to test this hypothesis. You think the company is being dishonest, and that, really, there are less than 12 ounces of liquid in each can. The alternative hypothesis, the claim that you would like to prove with data, is that mu is less than 12. Assuming a normal distribution, we can set up a graph under the assumption that the null hypothesis is true, centered around mu equals 12. Then we will go out and take a sample. If the mean of that sample comes up close to 12, perhaps 11, that might be considered relatively consistent with the null hypothesis, depending on the standard deviation and the sample size. But if the sample mean comes up really small, maybe something like 10 in the left tail of the distribution, that would be good evidence against the null hypothesis and in favor of the alternative hypothesis. We call this a left-tailed test because the null hypothesis is only rejected if our sample statistic falls somewhere in the extreme left tail of the distribution. The probability associated with the tail shaded in green is actually called the p-value, but we won't discuss that in detail here. Exactly how far into the tail the statistic needs to be to reject the null hypothesis will be discussed in other videos. A right-tailed test is the same thing, except now we believe that the population parameter is greater than some stated amount. The null hypothesis is the same, but the alternative hypothesis is that mu is greater than 12. We only reject the null hypothesis in favor of the alternative if our sample reveals a mean in the extreme right tail of the distribution. A two-tailed test is used when we believe the population parameter differs in some way from the stated amount, but we aren't sure in which direction. This would be like saying we believe the cans of pop don't contain 12 ounces of liquid, but we aren't sure if the true value is larger or smaller than 12. In this case, the alternative hypothesis would be mu is not equal to 12, and we will reject the null hypothesis if the sample result falls into either of the two extreme tails of the distribution. Many textbooks use the convention that I've shown here, an equal to sign in the null hypothesis for all three tests, but there is an alternative method, which is the one I will be using from here on out. Suppose we want to truly make the null and alternative hypotheses opposite to each other. Instead of using equal to in the null hypothesis, we can use a symbol opposite to the alternative hypothesis. For example, instead of using equal to in the null hypothesis for the left-tailed test, we could have a greater than or equal to sign. The distribution is still centered at mu equals 12, but now the two hypotheses have covered all possible numbers, greater than or equal to, or less than 12. The right-tailed test, null hypothesis, could have a less than or equal to sign instead, to be opposite of the greater than sign in the alternative hypothesis. The two-tailed test doesn't need to change. Equal to and not equal to already covers all possible numbers. If we write our hypotheses this way, there are two important things to remember. The null hypothesis always has equal to in some form, either greater than or equal to, less than or equal to, or just plain equal to. Also, it's important to remember that the alternative hypothesis is what determines if the test is left-tailed, right-tailed, or two-tailed. We have a left-tailed test if the alternative hypothesis has a less than sign, a right-tailed test if the alternative has a greater than sign, and a two-tailed test if the alternative has a not equal to sign. I showed this example with the population mean, but hypothesis testing could be done with a population proportion, the difference of means, or with a variety of other values. Alright, my friends, that wraps up part 1 of our introduction to hypothesis tests. Join me in the next video where I will discuss type 1 and type 2 errors.